I think we should get started. I'll shift Hugh's questions for once I see him online. So first question goes to Vadim from SiFive. Vadim, what platforms are available for the RISC-V high performance cores evaluation?
Okay, hi Mauro, and thank you for having me here. We provide pre-compiled bit streams for several FPGA platforms that are available off the shelf. For the lower end cores, we provide bit streams for low end RT board, about $100, $150. For the high performance cores like the VIU7 and U8 that I've covered, the platform is the Xilinx VCU118. It's a big FPGA platform, and we provide a bit stream with peripherals and a lot of inside building blocks that one can bring up Linux within a day and start developing its application with artificial intelligence and etc.
Thank you, Vadim. Next question goes to Ketan. Ketan, we heard a lot about chiplets today. And how do you see the ecosystem for the chiplets evolving from now?
Yeah, that's a loaded question. So chiplet, I mean, if you think of chiplet as it's actually a piece of silicon that you can reuse, and in fact reuse for not only one customer but for multiple customers. So in that sense, the chiplet, what it requires is, you want to have the IP and the ASIC providers, as well as the foundry and the packaging team. They all need to come together to kind of provide a silicon that can be used by many folks. So in order to do that, I think the most potential candidates are, of course, the IP and the ASIC companies, which have access to the foundry and also have access to the design services. So in that sense, we think that OpenFive is well positioned because the set of IP that we have are applicable to the chiplet market. Specifically, we call HBM as a very first form of a chiplet for use cases. So yeah, I think to answer the question, in order to enable the chiplet market, essentially the IP-ASIC team and the foundry and the packaging team needs to partner up and provide that to customer cost effectively and reliably. Yeah.
Thank you, Ketan. So the next question goes to Hieu. Hieu, how is EdgeLab's digital twin platform different from the traditional simulation and validation methodologies that are out there?
Well, listen, Mauro, you still need the traditional method. I mean, it's something that's been true and tried, and that will continue to be part of your validations process. But we can all agree on the fact that the environments and the situation in which connected vehicle are going to be deployed are hugely complex. So, instead of the traditional approaches, or in addition to the traditional approach where you have test vectors, pre-canned test vector that you apply to the device on the test and then comparing it with the certain output, you want to be able to first have an environment that you will be able to capture real world data that then you can use in what we call open loop type of testing, right? Same traditional kind of testing. But second, you want to also be able to have the device and the test be able to interact with real world stimulus as they occur. And the best way to do that is really to have it be inside of an environment that is closely resembling what happens in the real life. And that's what we offer with EdgeLab, both from an ADAS traditional type of onboard devices point of view, but also from a connectivity point of view, in terms of how the vehicle will interface with external components and peripherals and streetlights and signs and things like that. we see a huge opportunity with regard to that overall ecosystem and infrastructure that are bringing together interests from multiple parties, from cloud vendors, from edge device vendor, and from the automotive maker. And that makes it hard for any one particular provider to be able to really encompass coverage for everything, right? So hopefully that makes sense.
Yeah, thank you, Hieu. So the next question goes to Marc. Marc, why should someone choose a DDR5 or LPDDR5 for an application?
Yeah, so good question there. The DDR5 and the LPDDR5 memories are different on a couple of different areas. The DDR5 memories are really designed to live on a DIMM, and DIMMs are designed in many cases to go, multiple different sockets on the PCB. So with DDR5 devices, they're typically provided as narrower devices, usually 4 or 8 bits wide, but still the same size die. So it might be an 8 gigabit or 16 gigabit die, but provided with just a 4-bit interface or an 8-bit interface. With LPDDR5, you might have the same size of dies, but those are typically going to be provided with 2 16-bit interfaces per die. So the way that these fit into a system, the DDR5 devices will provide you with a lot more capacity for the same width, and LPDDR5 is going to provide relatively less capacity, which is needed for some applications, especially mobile and AI type of applications. So in summary, DDR5 if you need lots of capacity, LPDDR5 if you need more speed with less capacity.
Okay, thank you. And now there's a question for Andy. Andy, how can I figure out how much area embedded FPGAs will take on my chip?
Hi, Mario. Well, it's a good question. There's a kind of a quick and dirty way to do it, and then there's one that actually gives you more information. So the first thing you start with is an example design. And if you kind of listen to the talk, you really kind of want to pick something that's going to be representative of what you really want to put in the ASIC, whether it's an AI accelerator, encryption, or some other kind of custom function. You could take that and, if you run it through, Xilinx tools, it'll give you a resource report, and that will tell you how many lookup tables you need, or LUTs. And then with that, you can kind of look at how many, that design will take about the same amount of LUTs in our embedded FPGA IP. So it kind of gives you a rough order of magnitude estimate of how many LUTs you have. Each one of our cores supports 4,000 LUT4s. So then you can just do the math and try and figure out how many cores you need to form the array. The better way to do it is, though, to take that design, run it through our evaluation tools, and our evaluation tools will tell you exactly how many lookup tables you need. It'll tell you how many DSPs you need, and then how many flip-flops. And at the end, it tells you actually how many of our cores you need to execute that design, including what your utilization is. So with our patented interconnect technology, we can get 80 and above 90% utilization, which is quite a bit different than what you'd get with an FPGA flow, which typically averages around 70%. So you get a much more accurate figure of how big or how many of our eFlex cores you would need to support that embedded FPGA. It also gives you the timing information across the different process corners. So now you can go in with confidence in designing your chip, knowing exactly what your performance is going to be and how much area is going to take up.
Thank you, Andy. So now we're back to Vadim with a new question. Vadim, I want to get hold of a high-five unmatched development board. How can I do that?
Well, stand in line. The initial couple of boards were shipped to leading customers and our partners for tools development, but the majority of the boards will take another 2 to 3 months to get to our suppliers like Mauser, and then you will be able to order it online. But it is a big line.
Okay, thank you. Now a new question for Hieu. Hieu, is the digital twin environment applicable to every stage of the design or just to early stages? And does it extend into other areas of the product development and deployment on top of the design itself?
Well, Mauro, one of the examples that we gave is to be able to utilize the twins for instance, ISA exploration. You wanted to see what sorts of an impact a new or different ISA would have on your design all the way to the application level. But it also has parallel use for software development. So with a software model that you deploy into the environment as a twin, you can now actually create real world application to interact with the environment, without having to wait until the ASICs or an FPGA versions of the implementation is ready. Going further into your implementation process, it can be integrated into part of your DevOps lifecycle, so that whenever you have a new ingredient that's injected into your environment, you can now essentially execute the same test vector or a different test vector in the new scenario in order to validate functionality and to characterize performance of your platform. Ultimately, when you have devices that are already shipped and out in the market, keeping in mind that the connected vehicle should be deployed globally across the world, and you have different rules and regulations and environment that are constantly changing. So you need ways to be able to ensure that your devices are going to survive those type of evolution all the way down to obsolescence. So we're talking about anything from as early stage as ISA exploration, all the way into late stage support and deployment and beyond.
Okay, thank you, Hieu. Marc, now for you. It's similar to the previous question. Why should someone choose GDDR6 or HBM for an application?
Yeah, that's a good question, and I don't know, maybe Ketan might have input on this as well. But the decision is going to be, I think, it's a cost decision, it's a bandwidth decision, right? So HBM does really great when you just need a huge amount of bandwidth and there's no other way to get there. HBM can get there. If you also are concerned about energy per bit, then HBM is very efficient from an energy per bit basis. But the issue with HBM is that the cost of the system it can tend to be quite expensive. So, there's a cost of implementing a silicon interposer and so on. If you already have a silicon interposer for other reasons, some die-to-die things that you might be doing, then HBM is a kind of more natural addition to the chip. But if you have a chip that is not intended to be used not intended to be used with an interposer, and where you have memory bandwidth requirements that are not as high as HBM, then GDDR6 is a great alternative. And then for lesser bandwidth and more capacity, LPDDR5 and DDR5.
Thank you. Ketan, would you like to add something?
Yes, of course. I think I agree with everything that Marc said. We'll add a couple of more points. I think HBM is definitely extremely low picojoules per bits, right? It is thousands of bits going across between the memory and the main die. In addition to that, I think the low latency is a very much key to the HBM. It provides an extremely low latency simply because the dies are pretty much built onto the package. So those are the two key advantages of HBM. And GDDR, of course, is a market for automotive. HBM cannot participate there at this point. So I agree with Marc. GDDR is definitely a play for the automotive market.
Thank you, Ketan. And now just the same again for the two of you. Let's start with Ketan this time and follow with Marc. What is the right memory for a server-based AI device?
All of them, all of the above. I think mostly the DDR has been conventionally used for the high performance, and then going to the HBM, which is the low latency and low power, and then the GDDR usually are applicable to the smaller set of units, like the IoT or inference engine. So I would say maybe not GDDR as much, but definitely DDR and HBM are the key to memory types for the servers and data centers.
Thank you, Ketan. And Marc?
Yeah, I'd agree. I would also draw maybe a dividing line between the inference engine and the training engine. We're seeing the HBM to be quite popular in the training engines just because there's so much bandwidth that's needed in the training engine. And you also need relatively fewer training engines in in an overall AI deployment. So if the server is doing some training of a network, we quite often see HBM as an application there. And then, like Ketan said, for the inference applications, it can be any of the above. Even we've seen LPDDR5 and DDR5 in there for inference, as well as GDDR6 and HBM in some cases.
Okay, so I think, thank you, Marc. This concludes the questions we had for this session. So thank you very much to all of you, and great answers, and thanks for now. We are ready to finish here.